Good afternoon, everyone. Distinguished guests, professors and friends, welcome to today's ceremony. First of all, thank you for joining us to celebrate this special occasion together. Before we begin, just a few quick reminders. Please make sure to silence your mobile phones and other electronic devices. As we are in the Assembly Hall, which is part of NTNU's heritage buildings, we kindly ask you not to eat or drink inside. If you need to use the restroom, you can find them in the next building or on the basement level of the NTNU gymnasium. Now that the basic guidelines are settled, today's forum, the lecture program of Nobel Laureate in Physics with Professor Didier Queloz, is officially open. On behalf of National Taiwan Normal University, I would like to extend our warmest welcome and deepest appreciation to everyone for being here with us today. Let's start this special occasion with a big round of applause for all of you. We are truly honored to have several distinguished guests with us today. Please allow me to introduce them. Think Cheng Cooperation Chairman, Mr. Thomas Deng. National Taiwan University Center for General Education Director, Dr. Chen. National Taiwan University Institute of Biotechnology and NTNU Developmental Biology and Regenerative Medicine Director, Dr. Xiaoping Lin. National Chung University Deputy Section Director for International Affairs, Ms. Ellen Xuan. China Medical University Dean of Global Affairs, Dr. Liao. We are deeply grateful to have all of you here with us today. Let's give them a warm round of applause. Now, before we move on to our next segment, we have something very special prepared for you. We are honored to have 4 talented students from the Department of Music here at NTNU. Ms. Wu Qingzhong, Ms. Hui Yuding, Ms. Yi Qifan, and Mr. Rui Qianli. They will be performing a song from Mozart called Divertimento in F major KV 138 for us today. Please sit back, relax, and enjoy the performance. Let's welcome them on stage with a big round of applause. our musicians from NTNU's music department for that performance. It was truly beautiful. And now we are honored to welcome the President of National Taiwan Normal University, Dr. Chen. Please let's welcome Dr. Wu on stage.
Distinguished Professor Didier Queloz, and Chairman of the International Peace Foundation, Mr. Laureate, esteemed faculty members, dear students, and honored guests. Good afternoon. It is my great pleasure to welcome all of you to National Taiwan Normal University for the Taiwan Bridges lecture series. This platform, rooted in the shared value of science, the humanities, and the peace, carries special significance of us, and we are deeply honored that NTNU serves one of the hosts. National Taiwan Normal University is one of Taiwan's leading universities, renowned for its excellence in humanity and social sciences. NTNU has established a strong reputation in scientific research, with distinguished achievement in fundamental fields such as physics and astronomy. NTNU remains firmly committed to academic excellence, international engagement, and nurturing the next generation of scholars. We are deeply honored to welcome Professor Didier Queloz, the 2019 Nobel Laureate in Physics. His groundbreaking discovery of the first exoplanet orbiting a sun-like star opened a new era in astronomy. His lasting passion for experiments and the search for life in the universe shows how curiosity and a sense of responsibility can come together, inspiring scientists around the world. For NTNU and scholars across Taiwan, his visit represents not only a chance to learn from a world-leading scientist, but also an opportunity to explore future collaboration. His commitment to international research and to nurturing young scientists resonate strongly with NTNU's core value and aspiration. Finally, I would like to extend my heartfelt thanks to all of you for joining us, and to the International Peace Foundation and the Song Hongyan Foundation for their great support. And today's lecture inspires us all to promote peace, pursue knowledge, and building bridges across our shared world. Thank you.
Thank you very much, President Wu, for your work and also for being with us today. Now, please, it's my great pleasure to welcome our Chair of Honor, Professor Hsing from Center of Astronomy and Gravitation. Please, let's welcome Professor Hsing with a warm round of applause.
Okay, it's my great pleasure to have Professor Didier Queloz here to talk about this role of science in building a global agenda for peace. And he told me he will talk a little astronomy as well, so you can expect that. And also, I think I need to mention one thing. Didier is also the founding director of the Center for the Origin and the Prevalence of life. That's very important, especially I want to emphasize this. Let's welcome Professor Didier Queloz.
Okay, well, first it's my great pleasure to be here. I didn't realize that I already been in this place, but not physically, because in 2019, I gave a lecture here remotely from actually my home. so it's the second time I give a lecture here. The one I gave last time was about exoplanet revolution, which is my research topic. This one will be a little bit different. On the invitation to be part of the service program that is being proposed here, I thought it would be an opportunity to bring my research work, or at least the elements that we're finding today, into something which is very, very Earth-centric, which is very related to us, which is the question of peace. So that's the reason why I attempted to develop stories about science and peace. And essentially you will see that my essential message is I think we need more science, really more science here, and I will elaborate the reason why for this. Okay, so let's start with some elements just to set the scenery. If you think about science as a process, and actually it directly derived from our brain, for the level of consciousness that we have, which is pretty quite surprising. It's a process, very well organized, which is actually triggered by something which is part of us, which is our own curiosity. So if you want to qualify somebody doing research in any way, it's about curiosity driven. So it really is kind of a strong push to learn and to know what it is about. Now, curiosity is not enough. You need also to be able to imagine what you're going to see, and that makes us really extraordinary in a sense that we can do what's called mental projection. So we can build things in our heads. We can think about mathematics as well as an extension of our own brain. So science is about that. It's about collecting the element of curiosity, bringing the facts you can get, and making these mental projections. Now, what about peace? Then we're talking about a complete different element here. It's more about human interactions, actually. And that's not only human interaction, it's the nature of the build-up of our own species, which is the fact that we love being together. It's gregarious, called the gregarious nature of human-related species. And of course, when you're together, you need to have some level of organization, which I call the political aspect, but also there is the true nature of our own brain, which is what I call the social group behaviors. So you see here, it's rather different elements that are together here. On one hand, you have this capability of the brain to project and to imagine things. On the other one, it's just a practical element that you have to live with the others. And you have a lot of intrinsic, inherited, or built-in, or learned social group behavior. What is very interesting here, they both operate with the same CPU in a way, the same brain. But when you think about these two elements together, you realize they have not progressed the same way. And I think this is certainly something that is a main worry right now, and I would like to elaborate a little bit this, to convince you we do have here a serious element here to consider and to think a little bit about these two elements together. Well, the first, I'm always making this, we have to acknowledge that science has produced a tremendous amount of knowledge. I don't want to list all of them, I just want to point into, I think, the most main element that we are built on a couple of hundred years of science. Science is older, but essentially the last 300 years is. we have completely changed the world populations by being able to save most of the babies. Most of the baby would die very young. No, it's kind of a solved problem. Most of them, they live. It's very rare if you have the proper care to have it. We have mastered the power of the sun. Well, that's more the bad side away, because we produce so much power, which no one can have the power of self-destructions, but that we master in a way part of the law of physics of the universe. We have solved a massive problem. There was a food problem. Food problem has always been a massive issue on Earth. The human has been starving all over the time, and food has always been a strong focus for the society. And essentially, now we have the means to produce food for everybody. It doesn't mean it's happening everywhere on Earth right now, but we have the technicality to do that. It's also thanks to science that we have reached this level. And it's also thanks to science that we have left the gravity of our planet not so long ago. Well, all this happened in less than 100 years, essentially, built up. It's a tremendous change when you think about the global evolution of our species here. So in a sense, science has been tremendously successful, we have to admit. And we have become very, very powerful on this planet as well. Well, first, when you look at the growth of world populations, for a long time, it was a very, very slow scale. That's log scale. And essentially, thanks to the advancement of the knowledge of medicines, it has completely changed that. We are a very successful species in a sense, being able to grow and solving most of our intrinsic problem in the build-up of our species. So we're very powerful, we're very successful. And we are so successful that we can even change the planet. We have done that since a long time. It's something which is well known. If you look at the change of the amount of carbon dioxide in the atmosphere for the last 1,000 years, or you go even get back to the last 100,000 years, if you look at those species, it went up and down, depending on the temperature of the Earth. It's connected to the temperature of the Earth. And actually, this connection between temperature of CO2 is something very profound into our planet. You see this diagram on the top. You have the amount of CO2 going up and down, and you have on the bottom the temperature anomaly, the change of temperature. You see they're very correlated. They go up and down, up and down. It's not just random. It's just the practicality of the way the system works. What happens is, when you build up the CO2 in the atmosphere, it rises the temperature. Because we have more water, we have water on planet Earth. There is more water that is in the atmosphere. There is more water raining down, and that brings down, actually by the raining, the CO2. This rain of CO2 is going to drag the CO2 onto the rocks, dissolve the CO2. That's quite often a problem. If you boil hot water, you know that you have this solidified leftover line which is connected to the boiler, so you have to remove that. That's related to the same phenomenon, just the reverse mode here. And you drag it down, so you're going to wash and remove the CO2, and then naturally, by removing the CO2, you will decrease the temperature. So this kind of balance is being done, which is a mechanism of the plate tectonics that maintain this balance on Earth. Since quite long, we have this effect. They are maintaining the kind of a stable temperature, which is quite extraordinary when you think about this mechanism. Well, we're so much powerful that now we're changing this, and you may be aware, it's very spectacular, that the amount of CO2 that we have built up in the last 50 years is just spectacular, and we have these beautiful carbon dioxide concentrations measured at Mauna Loa observatories in the last 50 years. I think that's pretty much a spectacular number. So I just want to mention, I don't want to talk about global warming now, but I just want to mention that this build-up of knowledge we have acquired is just extraordinary. It gives us an extraordinary power. We can change the temperature of the Earth. Unbelievable, if you think about this. We can destroy a big fraction of the Earth with the power we have. We can cure, we can understand how to develop life. So it's quite a fascinating moment of acknowledging whether it's good or bad. I don't want to enter into a moral element here, but just to show how successful the science has been about solving a lot of problems and doing things. Now, when you think about conflicts, I did a bit of looked in the back and tried to understand a bit the history of this. And there has been a couple of work trying to do something very simple, just to count how many conflicts there has been in the last 500 years. Just count a bit. Just to show, get a feeling how far things may have evolved. Naturally, I would have expected that with a better knowledge, better understanding how to interact on the planet, better knowledge of how to interact with the other part of the human species on Earth, and building up this kind of global interactions. We're talking about global interaction, global exchange since quite a long time ago. The number of conflicts would have evolved and would have decreased with the time. And I was really shocked to see it's flat. The number of conflicts in the last 500 years, this study that has been done by the back catalogs, has not changed. So to me this is fascinating and very scary element here, because the amount of knowledge we have collected in the same time has been spectacular. But the way we interact in terms of society, social organizations, not. I'm not even talking about the nature of the interactions or the system of interaction. It's just the true nature that is leading up to conflict. And that is a serious issue, I think, here. And it really was a good opportunity to develop this element here and to think about what does it mean practically? What does it mean from my own perspective, from my own way to approach the problem? So what I do see here is a possible catastrophe that may not be in a very far future. It's clear that knowledge made possible by science has enabled us, let's call it extraordinary capabilities. I'm not making a judgment value here. And there is no sign that is going to slow down. So the idea that we will reach a limit, I think there is not a single sign of it. There is as much mystery in the physics that there were 100 years ago. They're just a bit different. And I'm not talking about medical science, understanding of life, chemistry, or they are the different challenges, but they're still the same. It's whether you have to go smaller, bigger, or hotter, cooler, whatever, there is a different way to understand that. So we'll keep finding things, we'll keep discovering things, we'll keep improving our knowledge, we'll become even more powerful, we'll have even more impact on the planet, even more easier, even more faster. There's no way it's going to change. On the other hand, the progress we have made in human sociology, understanding each other, it's not the single psychological element here I'm talking about. I'm talking about the collective human behavior. It's more social sciences have not. We don't really have change. We don't have made any progress in the conflict management. Not a single progress in the last 500 years. So, what does it mean for this? And I wanted to elaborate a bit on this, bringing back the astrophysics perspective. I think this dysfunction between our own pattern to operate with each other, it seems impossible to operate in a peaceful way. And the fact that we're growing the knowledge, becoming a tremendous risk for us. And I would argue that they may have some hint that this risk may be really real. And to do that, I have to move in a completely other topic. The famous Fermi paradox. Enrico Fermi is Nobel Prize in the late 40s. During the discussions about his colleagues, They discuss civilization, extraterrestrial, chance, life in the universe. And Enrico had this very famous statement, well, if this is so easy to our life, they must be everywhere. Where are they? Where is everybody? Was his famous sentence. This question has been looming around for some time. People have been really trying to find out whether there is some evidence of life outside the Earth, this famous, where is everybody? And we have to admit that right now, we have no signals, we have not found anything relevant, looking at many systems, many stars around. We have seen no probes, despite maybe a more recent claim, which doesn't really let us too much doubt. I mean, this is just a piece of rocks that went from the outer part of the solar system. We have not detected any megastructure, at least in all the probes we have sent in the solar system, so there is no monolith, if you like, Stanley Kubrick's stories, somewhere. We have not seen anything like that in the system. Everything looks pretty much natural in a sense, and there has been no visits. When I got discussion with people, they say, yeah, but you know, there may be visit, but we don't know, there is no, people are hiding this. Well, look, if you're really a civilization, advanced civilization, and you come to visit Earth, I'm not sure I want to visit a remote country. I would go directly to the right place to talk to the people. Could be university, could be United Nations, could be some main countries, whatever, but you would not go with it, you not die. So this is where we are, and you have to ask me right now, we're really completely alone. But I think this idea of alone life on Earth in the last 20, 30 years is changing very fast. And then we may end up with a bit more advanced data on this that we think. And then it will have consequences for the question I was asking before. And I will come back on the question at the end. Before, I just want to convince you that actually the idea of life in the universe is very common. Well, the first evidence I have for that is just look at the sky. Look at the number of stars you have, the number of options to have solar system. This argument has been developed many times ago, many times. People were not sure about the statistics. There has been some belief formation of planet would need a colliding stars, and it would be very rare, but there's no way to do that anymore. We don't know, we know that's not happening like that. It is really the leftover from the stars, which is making a disk and making the planet about. So you have so many stars in the galaxies. The number we're talking about are gigantic. I mean, this is 100,000 billion stars, gigastars in our galaxies, not giga. So there's really a lot, really a lot. Now, what makes this even more interesting is the solar system is pretty young in a sense. It's only 4.5 billion years old. The galaxy is certainly at the age of the universe, a bit later, maybe 1 million years later, but essentially it's almost the age of the universe. So there must have been many generations of stars in the past, because a star like the Sun would be in this state about 8 billion years. So we can imagine many generations of stars before. So we're not the first one. So many. So when you think about the number, it's so extravagant that it's just impossible to imagine that there has not been life developments on the planet. And I will have to develop that a bit further on. There are Earth scientists in this audience, so you're familiar with this picture, which is the history of the Earth through time. So it's like a clock. You start at the bottom at 6 o'clock, you go around. The reason why I show that is to make sure that you understand that when you talk about the planet, there is a whole storytelling when you go back to the history of that planet. The Earth didn't pop up like that at the beginning. At the beginning, it's more an astrophysical object and needs to be formed in this famous state I was mentioning, this proto-planetary state where you have a lot of material around and you have to assemble the planet. When you make the planet, it's very hot because it's just the pressure. You which is the energy of building the planet. There's a lot of gas that's going to disappear, but it's also a lot of stuff which is falling on the planet. And that's very interesting because actually there is a lot of carbon in a form, more an icy form into the cometary impact, falling into the Earth, bringing a lot of carbon. The reason why we have so much carbon on the Earth is possibly one of the reasons here. So it's quite carbon rich, the surface of the planet. Then it cools down, and when you cool down the planet, you end up with something which is not at all like the Earth. It's an atmosphere which is essentially based on what you have on the crust interacting with the atmosphere, in the case you have an atmosphere. Luckily, we have a lot of water as well, possibly from the beginning, that's what we believe right now. And a carbon dioxide atmosphere. It's very interesting because already from the beginning we have this carbon dioxide right there. And then something happened. All this stage took a bit less than 1 billion years. After 1 billion years, life is on the planet, is there. And this is this famous stage just before, called prebiotic, and then life is going to change everything. It's going to process a lot of the elements, typically the carbon in your body, of course it's processed by life, but carbon everywhere on the planet is processed for life. That's when we use it to test whether there are something that come from life related, the carbon-14 trick. So the planet is completely changed. So there is a concept here behind this already, which is interesting, is very early on, the conditions are met for the life to assemble and to start on planet Earth. So this is a very important findings because it tells you that if there are planets in the same situation that planet Earth, maybe the same process happened. And what is beautiful in astrophysics is we may not be able to go to these planets, but we can observe them technically. Nothing prevents us to observe them. There's a bit of delay of light to get in, but if you don't go too far away, the delay will not be tremendous. And you see 3 different stages on the right of planet Earth. Before life, it's the Archean Earth, kind of this atmosphere, which is before you have the prebiotic elements. Then when you start having life, but life is not really very visible, Proterozoic Earth, and then you have the modern Earth. If you look at the signal, which is here, there are spectra, response spectra, it's all light, looks like a different wavelength. And I don't want to go into detail here because they are the molecules that are going to trap some of the light and prevent light to go through. What I would like to attract your attention is the shape of these 3 diagrams are very different, but not different in a small detail, they're massively different. So the idea of astrophysics is pretty simple, is give us a planet, we can look, and give us a white telescope. We can tell you what the planet is made on the surface. And this opens questions about the capability we do have to look for different stages and different elements of origin of life. So right now I cannot tell for sure that life was present in many places, but what I can tell you is we can look for it on this kind of element there. Now, with the assumption life was very early on Earth, you have this idea that it must be easy to make it. There is a serious building blocks where people are trying to assemble there. These are the 3 contenders right now to make this work. The principle is you have to start with chemistry with a lot of energy and let the energy going down by making the system more complex. You're trading the energy you have in the molecules into something more complex. The 3 experiments you can do, one of them, in any case you need energy. One of them is you use the bottom of the oceans. There is ways to make some interesting complex chemistry there. There are some challenges into the nature of the dilution you get. It's not the most perfect scenario right now. The famous Liao experiment, as you know, the challenge of this is electric discharge into a gas. The problem is to make this work, you need to have a high energy into the atmosphere. which is not what we know happened on early Earth. The energy is called the reduced level for the chemist, was not enough to do that. But if you receive a big impact of a comet or big asteroids, which is quite frequent at the beginning, it can for a moment rise up this level and create the condition to have the Miller-Urey experiment working, so maybe it plays a role. The most recent development, the spectacular development in the last 10 years, is what's called the cyanosulfide chemistry. It's HCN. HCN is a deadly molecule. You don't want to work with that if you're in a chemist lab. It would kill anybody, just tiny bit. Extraordinary energized molecules. And you have the key ingredients, the C and the N there. You just have to find some phosphorus somewhere. And then this is where there has been a whole scenario developed on that, with the idea of the energy of the molecule combined with the UV radiation you get on the surface of the Earth, because you don't have any ozone at that early stage, make the early chemistry possible. Since the ingredients of life are essentially very simple and produced in most of the stars and live everywhere at the same time, there is a high possibility that life is created in any planet that have a minimum of a similar condition to the Earth at that moment. It's kind of a complete new to approach a problem. We start by the idea that life is extremely common, at least the beginning, to make it work. Because what you need is very simple, actually. It's not very complicated. What is a bit more complicated is you need to have life which is being installed and being developed. And just to convince you that the trace of that, this is a famous stromatolite. This is a bit the way that we would love to detect life. This is a trace of microbial activity which is left in the rocks. This is ancient stromatolite, fossils, and of course the modern one, which is in Australia. They are still growing, still exist. You can do that with cyanobacteria. There's a lot of this development, the leftover this in the rocks. And that's what we know at that moment. Life was not only just poorly working, life was massively in operation. Because to get bacteria able to produce this, you need a complete working system. And it's just a pseudo-life system. It's a complete alive working system that you have here. And it's only 23.7 gigayears ago. So this is the main element for most of the people to believe life is very, very easy to start in this form. What becomes interesting here is to develop this argument a bit further down the line. That was 3.7 gigayears ago. But when you look at life in a more global scale, you have to look at the tree of life. There's many ways to do that. I think the only proper way for an astrophysicist to do that is to do with the time. Because the time is the essence here of the process. You cannot get rid of time. You have to consider time. This tree of life is combining the two. It's combining the evolutions, and you see the big species there, but also you have time. So when you are in the middle here, it's back in time, early birth, somewhere. And then you see the tree of life starting, and the evolutions, and going on, the diversity, and the more you get closer to the edge, which is the outskirt of this tree, the more it's close to now. So today is the outside of it. So today we have all this diversity here. Human is just here, and just nice to remind you, it's here, with the last to come, here. Yeah. Now, I show that because there's an amazing message just by looking at this diagram. Well, the first, if you have to look at our ancestors and pay due respect to them, dear bacterians, they are the most ancient living organism on Earth. They are on this planet way before all the rest. They're there. Whatever happened on the planet, they don't care, essentially. You see? They continue. And it becomes a bit more complicated later when you develop more complex. The explosions of the Cambrian come much later when you have all what we are more familiar with. This is the Cambrian is here. It comes only the 500 million years ago. Only 500 million years ago we get these Cambrian explosions with the animals, and then what we're more familiar with, fish, amphibians, reptile, birds, mammals, much later. Only 500 million years ago. So for 3.2 billion years, you end up with something which is left. Bacteria, the plant, the fungi, and then the protostorms there. Protostorms, you may not be familiar, but it's an amazing family there. They've been everywhere. That is really interesting because you realize that life doesn't wait for us, essentially, to be there. But when it becomes a bit more bigger, massive, then you start to see some problems happening. The massive extinctions, they're pretty visible here. You see them, there are big gaps into the system here. It doesn't affect the bacteria and the archaea, but it does affect the big animals. So in a sense, I want to be a bit cynical. The extinction doesn't have any impact on life. It may be just good sometimes to reshuffle the dice a little bit. Think about us. Maybe we'd not be here right now without the extinction of dinosaurs, whatever they come from, the extinctions. So there's always this concept that life is this kind of continuum, complex, but the very complex life comes very, very, very at the end of it. And that is where it becomes more complicated. Because you can imagine a planet that produced life at the beginning. It doesn't mean that all the ingredients to maintain life and development of life will be met to create this complexity. One of the key ingredients was the rise of oxygen. So you see this time scale, 4.5, this typical age of the solar system. Life starts somewhere, 3.5 years ago, we had 0 here. And then there is the oxygen level. We have nothing at the beginning, essentially nothing. And then you have this big rise. There's a big debate what exactly it is. We know it must be related to photosynthetic phenomena, but it's not only this, there may be different elements that play together here. The data, you see really the data here, so it's not that simple. If people believe it's nice rise, and no, you see there's still a very active field of research, this oxygen rise here on the Earth. But everybody agrees that when you have 2 billion years ago, there is plenty of oxygen. That's for sure. Which is fine because we know at that time there is a massive, life invented the photosynthetic processes. Of course, this enables new stuff. Of course, to really move to the more complex animal, you need to reach the other stage. You still the last push you have here, and 500 million years. Whether there are something which is needed to create then the Cambrian explosions, or whether the Cambrian explosions is a result of something else that also created the oxygen, we don't know this. But you see already the very interesting story. So the oxygen, the idea to get oxygen, it's a very gradual process, and maybe you need time, or maybe you need something special, cometary impact, anything that is going to create or trigger something, or maybe a massive situations. Maybe you heard about the ice ball event for the Earth. There is an idea that maybe the Earth was covered by ice at some point. There is not clear evidence for that. There are some elements, but it's not completely clear-cut. Well, maybe you need to go through some process that enable that. And then you start to think about life has maybe been common as started, but the idea to get this evolution of life becomes much more uncertain, because the element you need to put together to enable it becomes a piece of luck, a really piece of luck. And at the end, to have all this process going on, you also need a long time. You need this time scale to get it. Again, only 500 million years. Now, I would like to jump now to something that has changed a little bit this perspective. That is the situation on Earth, and you get the Earth picture, what happened. Now, the slight change is we know for sure that there is thousands of planets. It's a sole problem. Planets are ubiquitous everywhere in the galaxies. So you cannot get a star without a planet, essentially. And you get one, no, you get 2, 3, 4. Maybe some stars they don't, but most of them should have a planet. Maybe they're just too small, right now, to be seen. So the idea of having planets, it's kind of universal right now. Planets is great, because if you want to do chemistry, you need liquid, you need a solvent, right? Gaseous chemistry, gaseous chemistry is complicated or cold and ice. Interstellar chemistry is complicated also as well, so it's better to have a solvent. Water is a great solvent. It's not the only one, that's a great one. To get water in liquid form, what do you need? Pressure. What do you need to get pressure? Atmosphere, planet. So that's why we love planet. It's perfect chemistry lab. So think about this idea. Remember, 100 billion stars, right? The galaxy. Or maybe I give you only 1% are really good. I have a system with rocky planet. Still 1 billion. So we have 1 billion labs, chemistry lab. All a bit different. They all have a different chemistry. They have the same element, but not the same way. Maybe some want more water, less water, whatever. So think about how many possibilities you have to explore about life. So is there only one kind of possibility, or is there many possibilities? We don't know. But this idea of the multiplications of the options you have is fascinating. And why we are so fascinated by the options? Because we already know that the diversity of the options for life development happen on Earth or on the solar system to be true. These are three planets that you all know very well, right? Venus, Earth, and Mars. It's about the size, right? Venus and the Earth are twin sisters. Let's call it sisters or brothers, whatever. They're same mass, same size. Mars is a bit different. Size shrunk. Bit of a problem of gravitation on Mars. Lost most of its atmosphere. But essentially, they are the same planets. They don't have dramatic difference. In the detail, they do have a lot of differences. Mars, as I said, not enough mass. So the first billion years was fine. There is water on Mars, there were a lot of water in the past, but because of the lack of gravitations, and also the fact you have solar irradiations, the combination of the two, so the combination of the lack of gravitations and the fact of solar irradiation has gradually removed all the atmosphere on the surface of Mars. Well, there is no atmosphere. Still water, but no atmosphere. Venus is a big mystery, because Venus is under a cap of clouds, and if you want to get down the cap of clouds, well, there's so much carbon dioxide that because of the nature of the chemistry becomes very deadly acid, and it's very hot on the surface. We can definitely not, we can maybe land something, but it's not going to stay very long to work. And we don't really know what is on the surface of Venus, but we know it's rocky. But we know for sure there is no water. There is no water on Venus. How come there is so much water on Earth and no on Venus? So some people may argue, yeah, it's fine if you have a greenhouse effect, at some point it will be so hot, the whole water will disappear. It's true. That's a possibility. But why do you have that greenhouse effect? And then there is the idea of plate tectonics, maybe magnetic field, because magnetic field protect the radiations as well from peeling the atmosphere. Now Mars gets peeled also because there is no magnetic field on Mars. So you start realizing that Earth is a bit special because they had the water, they have the magnetic field, it's cool in protecting ourselves. Maybe Venus didn't have enough water at the beginning, not enough. Not enough to have the plate tectonic working properly, because you need water to make it work, the oil, the mechanics there. Never really be able to recycle, like we have this recycling of CO2 I saw before with the temperature on CO2. So you see, it's not enough to be a planet that looks like the Earth. You need other elements as well. You can maybe start life to a point, and maybe there has been life on Mars and Venus before. There is this hope that Mars, for the first billion years, had oceans, and I think it's a fair idea to keep in mind. We now have evidence that there has been water in the past on the rocks. We don't know for Venus, if you, one day we'll land on Venus for sure, and if you find granite, for example, granite, you will find that there's been water, you need water to make granite. It's kind of element that can be done to find out, and we're going to find out that maybe in the first billion years of the solar system, we had 3 planets full of water. Maybe life started on the 2 planets at the same time, or ish. Maybe we had life development, early life development, and there has been a claim recently that they may find some traces. And this thing is not crazy in the sense that the idea of finding impact on the rocks due to bacteria is something we do have on Earth in the first billion years. So we can really realistically hope to get a trace of bacterial activity if there has been bacteria on Mars as well. So all this is trying to tell you that the idea that life is pretty widespread as a kind of an effect that is possible may be real. And in the next couple of years, we will find out that life is a bit everywhere on many planets as soon as you have the minimum conditions like this one, and there are so many of them. So it will be a kind of clear that life is a very universal effect. And that is kind of an interesting thought when you have this, because then you imagine this many kind of life. Now, what I will do in addition, I will show you that the diversity of the planet is even bigger than these 3 cases we have. And you can imagine different scenarios, different chemistry, different conditions that could make life even more diverse in its capabilities. There's a famous diagram in the planetary science, planetary science, is all the planet in terms of size and mass. This is mass and size and period. It's a very famous diagram. You may have seen that many times. I want to show you this to show that we have all these thousands of planets that are either the mass and the size of the Earth. You see this radius and the mass, and then different periods. Most of them close periods, short periods, so they're hotter because they're easier to find. We have this huge diversity right now, and we know that there are certainly some of them that have good conditions in terms of thermal conditions that could be compared to the Earth, because the sun, when they orbit, is much cooler. So even if you are close, you can still have good conditions. The challenge is we are limited right now by the discoveries of planets as of today, and we can only find the one which is on the left side of this kind of line that I have here. We cannot find something exactly like the Earth, and we would love to have something like the Earth. But it's just a matter of time, because the progress is definitely possible here. And the progress is really triggered by this idea that there must be a lot of conditions to have life, and why not having life on this planet? What makes this even more interesting is when you look at the likelihood to have a planet. We know that there is almost 100% chance, 50-80% chance that a star have a planet like that, the small spare planets. And it means, okay, we don't know for the Earth, exactly for the Earth one, but maybe these systems have also Earth-like planet. That would be fascinating to imagine systems. Imagine a solar system that you have. We have nothing beyond Mercury, but you can imagine a system that have a couple of planets closer to Mercury, and then Venus, and Earth, and continue Mars. And you can imagine many things. Maybe you can imagine this system, but they won't have life. Or at least they may start life, but life will stop at some point. Because, again, the conditions to have the time evolutions is not met. So I think this idea of time evolution of life is very the foundation of this. So people tend to shift a little bit the problem into life may be common, but maybe you don't have the time to get this. So the good news is we can get way more information on this planet we have, and this is kind of the last kind of data we can get now from this planet. This is atmosphere of planet detected. Planets are far away, they are about 100, 200, some of them are 500 light years. They are transiting planet. We use the size of the planet that we measure during the transit, so when the planet goes in front of you and the star, and we detect the change of size according to the color that we have on the detector. It's a bit like the sunset, the color change, so we get some different size for the planet, and this size can be turned into molecules. And we can detect a lot of these molecules that we have on the solar system. Water is very common in the universe, and we find again carbon monoxide and sulfur dioxide, all this. So all these molecules that I was talking about, they're everywhere. There's nothing magic. There's no specifics about water. Water is not something special. Actually, there's nothing more common than water in the universe. And of course, this is not exactly on Earth. This is a giant planet on the top. And the one on the bottom is a large Earth, which is just barely what we can do. That's the maximum of our capability right now with the telescope we're using right now. And there's been a claim that maybe there's a trace of life, but I don't think it's really serious with the detection of the dimethyl sulfide here. But I don't want to just elaborate on that. Just my point is to show you that actually the idea, the mental idea, that life is everywhere and can be tested in a very short future is very realistic. Of course, people are dreaming about detecting life in a late stage, as I said. And one of the ideas is, you all know this picture, this blue dot. This is the Earth observed from the far side of the universe beyond Neptune's. It's what's the name of these? I don't remember the spacecraft that did that. But anyway, so that's the picture when the spacecraft turned and took the picture. And what is nice here is not the picture by itself, is the idea that one day we should be able to do that on other stars. It's not something that looks invisible. Actually, there is ways to do that. We are developing a new kind of telescope. One of the biggest telescopes in the world is in construction right now. And that is the kind of picture you can imagine, not being the Earth here, but being another planet orbiting another star. And of course, what everybody is dreaming about is analyzing the light. That's what you get if you observe the Earth. You would get this kind of peaks and trough that corresponds again to the simple molecule I was mentioning, which is exactly the diagram I was showing before. It's pretty easy to do that if you see the planet, because it's very massive differences. If we point to a star with a planet and we see that would be a fascinating findings, because to produce such a signal with so much ozone here in that case, it means we have a high amount of oxygen into the planet, which means this planet should be in a stage which is corresponding to the last billion years on Earth, not the rest. Because most of the time you will not see the oxygen. You will see other stuff, but not the oxygen. That would be a tremendous findings, which means that life doesn't only process easily, it's also go to follow a similar path. It's called convergence development. We have seen that on Earth. So I mean, life has found tricks, different way, independently. The most famous case is the eyes. So the capability to be sensitive to light has been invented at different stage of the tree of life, without knowing each other. The nerves and the capability to develop the brain, complex brain, as well. We all know the story of the octopuses and us that follow very different branches, and octopuses has a disconnected, organized brain. Not only one, but as much brain that they have legs, but they still operate the legs very well together. It's a bit like a big network of computers working together here. So we know that the idea of convergent theory has happened on Earth. So the idea if the foundation of life is the same, if the nature to produce the units, the building blocks of life is the same, based on the same element, when you find the right similarity, not too exactly similar, but the right similarity with the Earth is met. And you can do that. And I think this is now time to go back to the beginning. At that stage, I hope I convince you that life is very likely everywhere in this universe. Life a bit more developed, a bit less, for sure. That's also something to bear in mind, because there may be some specific element along the way that's going to prevent us to reach that. Now, if we recap really what we have, this is a bit the way that I would see the problem we're facing. Okay, I think the first things that people tend to lean right now is this idea of the transitions to life is kind of embedded into what Christian de Duve, another Nobel Prize in biochemistry, considered as universe fabric. So the law of physics enabled this as a possibility. So because it's possible, like it's possible to make a star, or it's possible to make to produce all the atoms, or to make the chemistry possible. So the chemistry of life is possible. everywhere because it's part of the law of physics of this universe. So it should have happened and still happening many times in many places in the universe. There's nothing special on that. And that is what people stand to find more and more. The day when the first team of chemists will have cracked the code of the origin of life on Earth, and there are a lot of progress, I can tell you, on that topic in the recent 5 years, so it's very, very likely that this will be a solved problem in the next 10 to 20 years. That would be interesting then to revisit these questions. Now, the point is, if you base on the development of the evolution on Earth, what's called convergent evolution, so same trick has been found, different way, but different development of a tree of life on Earth, makes you believe that life finds its way, anyway. So they will find a way to develop the same kind of tools, because these tools give you a better survival chance. Sometimes they are complicated. When you think about the mammals, it's quite complicated when you think about, but the mammals are the ones that have best chance at some point to adapt to the change of the condition you encounter every time on Earth. Remember, if you look at the time of the Earth physics, whatever planetary physics, you can expect every 20,000 years kind of a change. When I say change, I mean a serious change. You can think about glaciations, you can think about have way more rain or no rain at all, it's even faster in some cases. So think about a species that could not react to such a change. It's dead, it's over. So either you have a way to evolve at that speed, it means you have to reproduce yourself many times per day to make the evolution working and adapt to a change at that scale. Or if you slow down your production rate, you will have to be able to cope with the change. You have all to survive, even if the temperature goes down by 10 degrees. Even if there is less water, you may have to be able to move to go elsewhere. This is why animal has been so successful at the end, and mammals as well, I think, because they have the tricks to react to that. On the other hand, bacteria are very successful because they have a very fast reproduction rates. So they don't need to adapt, they just evolve. They evolve very fast, and then by evolutions, then they can cope with any conditions. This is why it's difficult to fight virus and diseases, because by the time you find a remedy, they already evolved to the next stage. So that is really something that must have happened. It seems to be part of the system here. So I ask you again, so why are we alone? Because by now we should be convinced there should be life everywhere. So why are we alone? And I think we have three elements here to consider, which is interesting to have them written down. The first one is Earth is an extraordinary laboratory for life. And it means all what we have on Earth, including the moon, maybe the moon play a key role to bring the animals out of the sea, out of the oceans. The chance of the moon is very slim because you need to have an impact of something big enough on the Earth early on to remove a big piece of the Earth mantle, enough to make something big enough to create a gravitation effect, the tides, but not too much, otherwise you vaporize the Earth. So the perfect impact seems to have been something of the size of Mars at that time that produced the moon. Maybe for a planet like the Earth, the fact we have a moon is extremely rare, extremely rare, and maybe that play a role at some stage into the evolution. I just mentioned the moon because it's easy to understand, but there may be other element here in the same way. Maybe the magnetic field on the planet is very difficult to get. We have had a very, very stable magnetic field. It's not a given on the other planet of the system. It's a big mystery why Mars has no magnetic field. There's little magnetic field on Venus. We don't know Venus very well again here. So it's very, very interesting to ask this question. Maybe the magnetic field will stop. That would be dramatic. We die, essentially, if it stops. Because gradually the atmosphere will vanish. Because they protect us by the erosions of the atmosphere by high energy particles from the sun. Second, that's one way. So maybe we are unique on the galaxy. Because Earth is amazing. It's a possibility. Second one, it doesn't prevent the life to be everywhere, but it never reached this level. Never had the time, never had the conditions. So we'll find plenty of life, but nothing like us. Nothing that has this consciousness level like us. The second one is biology do not survive the space travel. I think this is real. We're not going to survive space travel. We know that. Everybody knows that there is no crazy astronaut that can go without a spacesuit into space. Right? So it's very dangerous. That's one of the big challenges to travel to Mars for the crazy people that wants to do that. It's just the irradiation of the sun. It's a very famous effect for the astronauts. They were very worried about getting trapped into main solar eruptions because they would be grilled essentially by the irradiations. So our biology is not designed for that. We're designed to stay on Earth. We need water. We need the right temperature. We know exactly what the range of liveness we can get on Earth. Maybe some virus survive some space travel, but they're not really fully alive system. So we know the limitation of that. Well, nothing prevents us to change, to evolve, but that's not our species. That would be a new species, not us. So that may be a problem, and you just can't do it. It's too far away. Just forgot. It's a possibility. Now we can still be able to communicate with them. So we have not found this, but there will be still a possibility here. Maybe we should keep trying doing this. The third one, which is to me the most likely given what we see today. When the species on the evolution of life reach a technological level such that they have power, there is a kind of disconnections, desynchronizations between the sociology they operate. Because our species has not really evolved. We are the same. The usual game I'm playing when I talk to people, I say, imagine I have a time machine in the back, which I can't get, but let's imagine, it's just a get-up experiment here. We grab a baby, a newborn baby, which is born with an old species, our own species, not another species, right? We grab it, we move it back now, you just give it to a family, you raise it, the baby will not know that it came from the human 100,000 years ago. Exactly the same. There has been no evolutions. Evolution came much earlier, 1 million year, 2 million year. There must be some intra-species exchange, definitely, with different humanoids species, definitely, but not in the last 100,000 years. So essentially we are the same that we had before. It was not too bad. The fact we wanted to kill our neighbor was not too bad. If you kill one or two neighbors, you kill maybe a tribe, it's okay. But the problem right now is the power is such that it's a complete different situations because the sociology that we still operate with had to handle such a knowledge, what we call the law of the universe, that we keep collecting. And there's so much knowledge that gives you so much power that sooner or later you misuse it, or use it the wrong way, or use it on purpose, the way you think you have to use it, and we disappear. This idea that when you reach this level of knowledge, there is an end game, because there is too much differences between the two. And I go back to my first statements. We have a major discrepancy. It was not the case 500 years ago, because the technology that you would get would not be good enough to create a massive problem. Even 100 years ago, would not. You would can kill millions of people, and there has been millions of people killed, definitely into major conflict. Massive bloodshed, and after, there's no doubt about that. But you will never kill the species. You will always have enough people still alive to do that. Right now, it's not the same. When you have, either by massive disruptions like thermonuclear, or maybe massive dysfunctions of the whole ecological system on Earth, we're going to kill ourselves. It's soon, it's for sure, if you don't stop this. That's absolutely sure. Now, the question is, how much time we have to do what? And that's my whole point, I think, here. We're entering the third millennium with so much power. Think about the last millennium. The power of people is completely different right now. So I think we will have sooner or later, if you want to survive in terms of species. Well, the good news is life will survive us. Again, I keep telling, don't wait for life. They didn't wait for us, they will not wait for us. It's just us, our species. We have to initiate a profound sociological transformations. And that's really the only way of survival here. How we have to do that? Well, I think we have a superpower, and we should really value and acknowledge it. I think the consciousness level we have is just absolutely fabulous. I call it a superpower. This kind of capability of mental projections. For me, it's a gift. It's a gift of the law of nature, it's a gift of the universe we receive. We're just not good at using it properly, I think. I think we are a global species right now, there's no doubt, and you can tweet, you can chat, you can talk to anybody, you can exchange information at a local level at the speed of light. So we are definitely a global species right now. We were already global in the sense we have populated all the places on Earth since the last 10,000 years, but now we can exchange so much that the Earth is not protected. That is why there's so much intra-species problems, because we created a lot of situations by moving things around so much that by moving goods we have completely flattened out all the natural dividing line between the continents and even the islands and everywhere. Even if you protect your islands and you meet at the entrance of Taiwan, they ask you, will you bring meat from China? I understand you want to bring stuff, but actually at some point later you will get it. Because there's no way. Too many people moving, too much things moving around. So we really have these global elements, but we have an instinct behavior which is very, very profound, which has evolved on a tribal mechanism. You call it the family, call it the tribe, call it the country, call it whatever you want to call it. But we operate as a tribe because it's the way we operate. That's the way we're designed to operate. We just protect things around us, other than close people, because we have the connections, we already have the emotional connections. It's our instinct. That's been also so much of a social species that is part of our survival at the beginning. We have survived because we were social. Now, what is the challenge here, and I will try to leave you with this, I think we have this kind of, I call it the irrational behavior, which may be a bit negative. And I don't see rationality as negative. I always keep telling that the creativity in everything, what is in science, in art, in music, is playing with your own irrational side. But never get trapped down on the rational side. So always a kind of a very, very difficult walk on the cliff. One foot on the irrational, one foot on the rational elements. And you have to play with the two because I think they resonate between each other. And this has to be better understood. And I know there is way more studies being done right now, especially it has been done for understanding the exchange, financial exchange. That's very practical, but people wanted to understand the pattern behavior of the people, how they deal with this financial exchange. It's one of the social issue behavior that I was talking about. This one is not creating conflict directly, but indirectly they do, essentially, because they create a situation where wealth is not evenly distributed on Earth. And they're also part of a problem, I think, here, specifically. So I think all this needs to be better understood. I do claim we have the tool to do it. We do have the tool because the scientific knowledge does not only apply on the universe, it can also apply to ourselves. It applies to our sociology. And when I'm talking with funding agency, I keep telling them, what is a fraction of the money when you give to the social studies to understand the pattern? The way they operate in a global as a species. And it's growing, this amount now of funding grows because people realize that we have a complete lack of funding and support on that. In a way, we have been spending too much money on understanding the universe and not enough to understand our brain, ourselves, and our social behavior. Not only the brain as an independent element, as a connected element that connect to each other and react to each other. So I think we have a way. And we should embed that into what I call social policy. I think we cannot let the policy dictated by politics, because politics is essentially rarely done on this element there. It's mostly related to the instinct tribes response that people organize, the way they believe it has to be organized. But sometimes it's very disconnected from the practical need of our brain. That's why you have revolutions and big effect that are changing all this pattern, and you create conflict this way. And we also find a way, being global, to respect the diversity that we have. Because whether we are a social beast, we are also unique in a kind of way to apprehend the world. That's the beauty of the consciousness. Together, We have almost 9 billion different consciousness together. So they can operate together. There are some common language that we can deal with. But I think science is one of them. Because we can share these mental projections. We can build them together. That make us an extraordinary species, I think. So to me, I wanted to leave you with this kind of note of optimism, aware of these disconnections, but also this kind of amazing mental change about the concept of life and how we can consider maybe the Fermi paradox as a tool to drive us to the point that we are starting a very risky time right now, and we should maybe spend a bit more time understanding the social connections between each other. I will leave you with this. Thank you very much.
Thank you very much, Professor Didier Queloz, for your presentation.